All right, here we're going to talk about systems of equations, but before I get into that, I want to just point out what we have been working with is just an equation that has one variable, like this. If there's one variable, you can always solve it. We can isolate that variable by doing inverse operations. We see that x is 2. But if we have more than one variable, like if I have negative 9x plus 3y equals 27, I can't just solve that for x and know exactly what the solution is. If you solve that for x, I'm going to have to move this 3y over here. So I would have negative 9x equals 27 minus 3y. And then I'd have to divide by negative 9. And I would have x equals negative 3 minus, or negative 3 divided by negative 9 is plus. It's messy. We don't really know what the solution is. All we did was shift things around to get x by itself. So if you actually want to see what the solution is, then you need to have a second equation that shares that same solution. So if you have two variables, you need two equations. If you have three variables, you need three equations. So here's a second equation. And there is a solution that these two equations share in common. And you know that it is a solution because it's true for both equations. So I'm going to tell you what that solution is, and we're going to go over how to find out that answer using three different methods in this unit. This is one of the solution to this system of equations because it is true for both of those equations. And what I mean by that is if I substitute in negative 1 for x and 6 for y, then I end up with the true statement. So for example, with this first one, if I put negative 1 in for x, I get this. If I put 6 in for y, I get this. And I'm telling you, if I multiply that and then add them together, it does equal 27. Because negative 9 times negative 1 is 9. This is 18. And 9 plus 18 is 27. That's what I mean by saying that those two coordinates are true for that equation. And if I substituted it into the x and y in the second equation, we would see it's true for that one as well. So one of the ways you can solve a system of equations is by graphing. So the red line here is made up of points where these points represent solutions to this red equation. That if I substitute in those x, each of these points, if I substitute in that x of 4 and the y of negative 4, it would work. It would be a true statement for that equation. And the same for my green line. If you graph it, this represents points for that green equation. So what a system or a solution to a system of equations is asking is what point, what solution do they have in common? And so when you have a graph, it's really just where do they intersect? They intersect at over 2, down negative 1. So this is the solution that my green and my red line have in common. That is the solution to that system of equations. If you're not given a graph, if instead you're given just some points that are solutions to that equation, like here in the top table, they substituted in negative 1 for x, and they solved it and said, when I put in negative 1, 2 times negative 1 minus 4 is negative 6. So that would be one of the solutions to that equation. Trying this one, if I put in 2 for x, 2 times 2 minus 4 is 0. So over 2 up 0. So they went through and they found some solutions to that equation. And if you have at least 2 points, you can graph it. So this is like what that graph looks like. And then for the next one too, they did that. If I put in 1 for x, multiply it and subtract 6, I got -3. So 1, -3 is a solution to that equation. And then, oh look, this one also has, when you put in 2, the answer is 0. Y is 0. Over 2 up 0. So sometimes you might be given those solutions in a table, and you don't have to graph it. You can just look and say, oh, they both have this point in common. That means it is a solution to both of those equations. That is the solution to the system of equations.